So the Erdős-Rado's conjecture on sunflower lemma is that if you have many sets, the exponential number of sets, c to the k, then you have sunflower of size k. Now, what if we restrict to the subsets of one of the integers from 1 up to n? Then can you say something about the lower bound on the number of sets in order to guarantee the existence of sunflower of size 3? So that's conjecture by Erdős-Szemerédi. In 1978, they conjecture that when you have a sub-exponential, if you have a, okay, let me write it down. Right, there exists a epsilon, universal constant epsilon, such that for all n, every family of subsets of 1 up to n with cardinality bigger than 2 to the 1 minus epsilon times n contains a sunflower of size 3. So sunflower of size 3 means that you have A, B, C, and F, right? So that A intersection B is equal to B intersection C is equal to C intersection A. And this conjecture is actually implied by Erdős-Rado conjecture. So what's known is that Erdős-Rado conjecture implies Erdős-Szemerédi. The theorem is, let me just state the theorem. This is due to Erdős and Szemerédi. Is that if the Erdős-Rado conjecture holds with C, then every family of subsets of 1 up to n with cardinality bigger than 2 to the 1 minus c over 4 n contains a sunflower of size 3. I'm not going to prove it, but so in a sense, if you believe the Erdős-Rado conjecture, then this Erdős-Szemerédi conjecture has to be true. Furthermore, there's a theorem due to Alon, Pilka, and the Umans in 2013 that if the capset problem, if the capset conjecture is true, then Erdős-Szemerédi conjecture is true. That was in 2013, but now by using slice rank, we now know that capset conjecture is true. Right? So now this is proven by Ellenberg and Giswit. So now this has to be true. Now it's a theorem. Right? We present a direct proof of this theorem, and this is due to Naslund and Sabin. So this is theorem now by Naslund and Sawin, which was published in 2017, which is as follows. Let F be a family of subsets of 1 up to n with no sunflower of size 3, then the cardinality of F is at most 3 times n plus 1 times sum of n choose k, where k is at most n over 3. And the proof is a beautiful applications of slice rank. Okay, let's see the proof. Right, so we map every subset to a vector, right? So map a subset of 1 up to n to a 0, 1 vector. Right? So n-dimensional, in an n-dimensional vector space. So let S be the set of, so this is called the characteristic vector, right? So the characteristic vectors of members of F. If F has no sunflower of size 3, then for all distinct x, y, g in F, no, not in F, in S, what's gonna happen? Well, it doesn't have sunflowers. That means x intersection y, so the x intersection y should be different from y intersection g, or y intersection g is different from x intersection g, or yeah, one of the 3 things, right, happens. Yes. So what does that mean? So it's not of this picture, right? So that means there exists I, right? There is some coordinate which belongs only 2 of them, right? So what does that mean? There is I such that exactly 2 of xi, yi, gi is 1, right? So there's an element belonging to exactly 2 of them, so that when you take an intersection, when you compare the intersections, so for instance, if it's a 0, 1, 1, then intersection of these 2 will have this entry I, will have this I, but intersection of those 2 will not have I, right? So that's the only possible way. So 0, 1, 1, or 1, 0, 1, or 1, 1, 0. All right. So this is the key idea. All right. So let SL be the set of vectors in S with exactly L ones. So I'm gonna define partition S into S0, S1 up to Sn. Now, what's next? we further claim the following. So the claim that for x, y, z in SL, x is equal to y equal to e g, or xi, yi, gi is equal to 0, 1, 1 for some I. Right? Because, okay, so if x and y are equal but g is different, so there are three cases. I mean, if x is y equal to y but not equal to g, then trivially there is yeah, so here's the key thing. Yeah, trivially there is now we use the fact that these vectors are from SL, so each of them has exactly one L ones. So if x is equal to y and not equal to g, then as all of x, y, z have exactly L ones, there is I such that xi, yi, gi is equal to 0, 1, 1. Alright? I mean, you may wonder why you don't have a 1, 0, 0, but if this is the case, so there is if there is an element, like if g has coordinate value 1, which is different from x, but then g must have coordinate value, some coordinate whose value is 1, no, 0, so that x has 1, because they all have a same number of 1s. Alright? So in this case it's easy. If x, y, g are all distinct, then since f has no sunflowers of size 3, there is I such that xi, yi, gi is 0, 1, 1. So if all of them are distinct, then it's okay. If two of them are equal but the last one is different, then still you have such a thing. Now that's the key idea. So we are going to define the function as follows. So now for x, y, g in SL, define the polynomial FL x, y, g as the product of 2 minus xi plus yi plus gi. Now there's no squares. Then FL x, y, g is non-zero if and only if xi plus yi plus gi is not 2 for all I, and that's if and only if x is equal to y is equal to g. Right? So that means by the lemma on the slice length of a diagonal hypermatrix, the slice rank of FL is equal to the number of such a set, which is cardinality of SL. Now we need the upper bound in the slice rank of this polynomial, and the technique is still the same. We expand this polynomial. So by expanding FL, we have we have a linear combination of monomials x1 I1, x2 I2, xn in. Now very familiar, right? J1 yn jn and g1 k1 gn kn, where now the only difference to this compared to the CAPSET problem is that also I see. So now you don't have square, everything is 0 or 1. And their sum is at most n over 3. Their sum is at most n, right? Because it's a product, and I mean the degree of this polynomial is n, so this cannot be too big, right? So by the Peasonal principle, sum of IL is small, or sum of JL is small, or sum of KL is small, right? Now we're going to use the same idea, by the same idea from the CAPSET problem revisited. In our previous video, we deduced that the slice rank of FL is at most, right, the number of ways of choosing these things, these monomials, well, 3 times, right? 3 times number of ways to choose I1 up to IN as a 0, 1 values, so that their sum is at most n over 3, right? So that's like how many ways can I choose k of these coefficient i's, so that they become 1 and the remaining become 0. That's like k, and choose k, and k has to be from 0 to n over 3. So that's slice rank. Now this implies that, and remember why we have this 3? That's because we will collect these monomials based on which of these things is true, right? If this is true, we have a slices of this many slices. If this is true, we still have this many slices, collecting terms in terms of y's. If this is true, then we collect terms in terms of g. So we have this many slices, for one for the x, one for the y, one for the g. So that's the slice rank. All right, so that means size of SL is at most 3 times sum of n choose k from 0 to n over 3. So the size of S is at most, this is from, I mean, I know that this is equal to S0 plus S1 plus Sn. So it's n plus 1 and this thing. Okay, so that's the theorem. It's a very easy proof. Once you know the technique, this is a simple theorem. Now, if we want to optimize this, how do we do that? How to optimize? Like how to estimate the growth rate? Now, we have this sum of binomial coefficients, so we use this binomial theorem. Now we are looking up to n over 3, so we divide both sides by let's say, well, let's do this way, x to the k. We divide by x to the k. Let's not use k, so I. And that's gonna be x to the I minus k from 0 to k plus n to the I x to the I minus k from k plus 1 to the n. Now, if x is between 0 and 1, right, then this term will be tiny. It's going to be less than 1, but still positive. So we can get inequality like n choose I, x to the I minus k. Now, and if x is between 1, since x is less than 1, this number is bigger than 1, right? So I can replace it by this formula. So this sum of this binomial coefficient is less than or equal to 1 plus x to the nth power divided by x to k. Now assume k is less than half n. And then we wanna choose some x to minimize the right hand side. And I'm gonna give this value x to be k over n minus k. I mean, one can try to apply the derivative and find the optimum. Okay. So if we plug in this, then what we get is sum of n choose I from 0 to k is at most 1 plus k over n minus k to the nth power divided by k to over n minus k to the k's power. All right, now that's k to the k and n to the k, right? So why? This n is coming from this term, right? So that's become n to the k, and then n minus k to the n minus k to the nth power, yeah, n minus k. Wait, something, yeah. Oh, right. It's here, right? N to the k is here, and then n minus k to the n minus k. All right, so that's, yeah, so if k is equal to alpha times n, then what we get is n to the alpha times n over alpha n to the alpha n, and 1 minus alpha n to the n minus 1 minus alpha n. Right, now when you look at this, you have n to the alpha and n to the alpha n together, so what we end up is alpha to the alpha n and 1 minus alpha, right, n to the alpha n, n to the 1 minus alpha n, so n to the, oh, I see, yeah, there was a typo here, right? So now yeah, this is n, right? This is n. Now n to the n is divided by all, yeah, so this term is cancelled with all these things. So what's left is alpha to the alpha n, 1 minus alpha to the 1 minus alpha n. All right. Now what is that? That is, that's what we have. All right, so this is now if alpha is 1/3, then so that's what we want, right? We are summing over up to 1/3 n over 3, so alpha is 1/3. Then sum of n choose I from 0 to n over 3 is at most 1/3 to 1/3 n and 2/3 to 2/3 n. All right. Now, if you compute this, what do we get? So 3 to the n divided by 2 to the 2/3 n, right? And if you compute it, you get something like this. So that means if you have a more than one, if you have a set of size more than, if you collect the subsets of one, if you collect more than this many subsets of 1 up to n, then you must have some flowers of size 3, which proves this conjecture, right? Instead of 2 to the n, now you have a 1.88988 to the n. So this proves the conjecture of Erdős and Szemerédi. Okay.